Welcome to the Explainer. Today, we're going to pull back the curtain on the secret language of science itself. I'm talking about how scientists can measure literally everything, from the tiniest atom all the way to a distant star, and do it with some seriously mind-blowing precision.
Okay, let's dive right in. We've all been there, haven't we? You tell your friends something is like 5 steps away, but your 5 steps are completely different from their 5 steps. And, for just chatting, that's fine. But imagine trying to build a skyscraper with that kind of system, or launch a rocket. It'd be total chaos. And that is exactly why science needed a universal language, a standard everyone could agree on. So, to get rid of all that confusion, scientists from all over the world actually got together. It was back in 1960 when they officially agreed on one single standard system for everyone. And this was a huge deal, a total game changer. It meant they could finally collaborate and share their discoveries without ever having to ask that silly question, hey, wait a minute, whose step are we talking about here?
And that system, it's called the International System of Units, or what we usually call SI for short. Honestly, you can just think of it as the ultimate rulebook for how to measure stuff. It's the reason why a meter in one country is the exact same length as a meter on the other side of the planet. And that's what makes scientific data trustworthy, no matter where in the world you are.
Okay, so now we get why we need this universal language. So let's actually learn how to speak it, right? We're going to break down let's call it the alphabet and grammar of SI units. It's easier than it sounds, I promise.
And you know what? We see this scientific language all the time, every single day. You go to the store, you pick up a bag of sugar, and what does it say? 1 kg. That kg, it's not just some random letters. It's a super precise amount, defined by that SI system we just talked about. And it means the exact same thing to a chef in Paris as it does to an astronaut floating around on the International Space Station.
So here they are. These 5 you're looking at, they're the real heavy hitters. They're the fundamental building blocks for pretty much all of measurement. And get this, believe it or not, there are only 2 others that make up the entire SI system. That's it. Just about everything else we measure, things like speed or energy, it's all just a combination of these basic units. Think of them like the primary colors of the science world. You can mix and match them to create everything else.
Okay, but what happens when you need to measure something really, really big, like the distance between 2 cities? Or something incredibly tiny, like the width of a single human hair? Saying a road is 1 million meters long, that's kind of a mouthful, isn't it? There's got to be a better way.
And of course there is. We use prefixes. You can think of them like superpowers for our base units. For example, kilo just means 1,000. So instead of saying 1,000 meters, we just say 1 kilometer. Easy. On the other end, milli means 1,000th. So a tiny fraction of a second becomes a millisecond. They're basically the ultimate shortcuts in science.
And once you get the hang of these prefixes, converting between units becomes super simple. Let's take 1.9 kilograms. Well, we know kilo means 1,000, right? So we just multiply 1.9 by 1,000 and bam, you get 1,900 grams. It really is just a simple 2-step dance. Figure out what the prefix means and then multiply or divide. That's it.
All right, let's try a quick one together. You ready? How many centimeters are in 0.13 meters? Well, remember that centi deals with hundreds, so all we have to do is multiply by 100. And the answer is 13 centimeters. See? Not so bad.
Okay, so knowing the language is the first big step. But a language isn't much use if you don't have the right tools, right? You wouldn't try to write a letter with a hammer. It's the same thing in science. Picking the right instrument for the job is absolutely crucial.
So take a look at these 2. On one side, you've got a good old-fashioned ruler, something we all know. On the other, a vernier caliper. Now, they both measure length, sure, but they work on totally different levels of detail. They're built for different tasks, and trust me, using the wrong one for the job can lead to some pretty big problems.
Really, what this all boils down to is a word: sensitivity. A regular ruler, its smallest reading is usually 1 millimeter, and that's totally fine for, say, drawing a line in your notebook. But a vernier caliper, it can measure down to 1/10 of a millimeter. It's just way, way more sensitive, which makes it the perfect tool for getting the precise thickness of something like a coin, or the diameter of a tiny wire.
All right, let's start to bring this all together. You've got the language, you've got the tools, but how do you actually use them perfectly? This next part is all about understanding the super important difference between being accurate and being consistent. And, just as important, how to deal with errors when they pop up. Let's use an analogy. Imagine you're throwing darts at a dartboard. Accuracy? That's hitting the bullseye dead center. Now, consistency, That's getting all your darts to land in the exact same little cluster, even if that cluster is way off in the corner and not on the bullseye at all. See the difference? In science, you absolutely need both. It's no help at all to be consistently wrong. The real goal is to hit that bullseye every single time. So what are the things that can throw us off our game? Well, first up, we have something called systematic errors. These are the kinds of mistakes that are predictable. They're always there, messing things up in the same way. The classic example is a bathroom scale that isn't set to 0 properly. If it always adds an extra 5 grams, then every single measurement you take is going to be off by that same amount.
And a zero error is probably the most common type of systematic error you'll run into. It's simple, really. Before you even start measuring, you have to check, does my instrument actually start at 0? If it doesn't, no big deal. You just have to remember to account for that difference in your final calculation. You either add or subtract that little bit of error to get the true, accurate result.
Now, the other type of error we have to worry about is random error. And just like the name says, these are, well, they're random. They're unpredictable mistakes that are usually caused by us, the person doing the measuring. Maybe you misread the scale by looking at it from an angle, or you hit the stopwatch just a little too late. These errors are inconsistent, and hey, they can happen to anybody.
The good news is you can totally fight back against random errors. To avoid something called parallax error, you just have to make sure your eye is perfectly level with the mark you're reading. But you want to know the most powerful technique of all? Just repeat your measurements. Take a reading 3, 4, maybe even 5 times, and then calculate the average. Doing that helps smooth out all those little random mistakes and gets you so much closer to the actual true value.
All right, that's enough theory for one day. Let's put everything we've just learned into practice. We're going to do a little challenge, and we're going to measure something you probably have sitting right in front of you, a textbook.
So here's the game plan. We're going to do this the proper scientific way. First, we'll measure the thickness of the book 3 separate times using a regular ruler, and then we'll find the average. After that, we'll do the exact same thing, but this time with our more sensitive tool, the vernier calipers. And for the grand finale, we'll compare the results we got from both instruments. And what do you think we'd find? Well, the ruler would give us a pretty good reading, but the numbers would probably vary a little bit each time. The vernier calipers, on the other hand, would give us a much more consistent result, and down to a finer decimal point, all because they have higher sensitivity. And if we broke out an even more sensitive tool, like a micrometer, our results would be even better. It all comes back to this. More sensitivity leads to better accuracy and better consistency.
So here's the big takeaway. Measurement isn't just some boring task you do in a science lab. It's this incredibly powerful language that lets us understand and shape our world with amazing precision. It's what makes the GPS in your phone work. It's what allows engineers to build computer chips with parts thousands of times thinner than a human hair. And it's what helps doctors calibrate the medical equipment that saves lives. It really does all start with mastering the language of measurement.